This single electric motor is more powerful than 200 family cars running flat out at the same time. It stands taller than a man, weighs as much as a loaded semi-truck, and it spins a steel shaft so thick you couldn't wrap both arms around it. No pistons, no fire, no exhaust. Just raw electricity twisting metal hard enough to turn a rolling mill that flattens red-hot steel, or lift a fully loaded cage up a mine shaft a mile deep. That's about 1.5 kilometers straight down. The very biggest of these monsters push past 100 megawatts. That's over 134,000 horsepower out of one machine. And here's the part that gets me. To build something that strong, with that much torque, a factory has to wind miles of copper by hand, bake it solid, and balance a spinning rotor down to a few grams. Stick around, because the way they make the most powerful electric motor on Earth is wilder than anything under your hood. Let's start with the scale, because the numbers barely sound real.
A regular car engine makes maybe 200 horsepower.
The electric drive motors inside a mining haul truck, like the Komatsu 980E, put out around 4,400 horsepower, and that's around 3,200 kilowatts, just to move 400 tons of rock. That's around 800,000 pounds. But those are the small ones. Step up to the giants that drive steel rolling mills and mine hoists, and a single synchronous motor from a company like ABB can reach 65, even 75 megawatts. That's up to 100,000 horsepower from one unit. And the absolute largest electric motors ever built, the ones used for pumped storage power plants and ship propulsion, climb past 100 megawatts. Picture this, a machine the size of a small room, quiet enough to stand next to, that produces the power of an entire highway full of cars. And it all starts with two things, a heavy ring of steel and a mountain of copper. The heart of the whole machine is the stator. That's the part that stays still while everything else spins inside it. And it begins as hundreds of thin steel sheets, each one stamped into a ring and coated so it doesn't touch its neighbor. Why so thin? Because if you used one solid block of steel, the changing magnetic field would heat it up and waste enormous energy. So workers stack these wafer-thin sheets, sometimes 1,000 of them, into a single core, then clamp the whole tower together. Now comes the part that turns a chunk of steel into a powerhouse: the copper. Thick bars and coils of copper get wound into the slots of that steel ring, loop after loop, layer after layer, miles of it on the biggest machines. Each coil has to be wrapped in insulation by hand, because if two copper wires ever touch where they shouldn't, the whole motor shorts out and burns. On a 60 megawatt machine, the copper alone can weigh several tons, and every single turn matters, because that copper is what catches the electricity and turns it into a spinning magnetic field. Once the copper is wound, the stator gets sealed. The entire thing is lowered into a tank and soaked in special resin. Or sometimes the resin is pumped in under vacuum so it creeps into every gap between the wires. Then it's baked in an oven until the resin hardens into a solid block. Now those hundreds of loose copper coils become one rigid, waterproof, vibration-proof piece. Think about what this motor goes through. It runs for years, sometimes spinning thousands of times a minute, fighting enormous loads, heating and cooling over and over. If the copper could shift even a hair, the constant vibration would saw through the insulation and kill the machine. So they lock it down hard. After baking, every coil gets tested with high voltage, far higher than it'll ever see in real life, just to prove the insulation holds. Only when the stator passes does it move on, because now they need the part that actually moves, the rotor. The rotor is the spinning core, and it's built around one massive forged steel shaft. On the biggest motors, that shaft is as thick as a grown person, and it has to be because all the twisting force of the motor, all that torque, flows straight through it. A weak shaft would simply twist apart. Around that shaft, they build the magnetic part of the rotor, either with more copper windings or with banks of powerful magnets, all locked in place to survive the brutal forces of spinning at full speed. And here's where it gets surgical. That finished rotor has to be perfectly balanced. They mount it on a balancing machine and spin it up, and sensors hunt for the tiniest wobble. Even a few grams out of place, multiplied by thousands of rotations a minute, becomes a hammer blow that would shake the motor to pieces. So they shave metal off the heavy side, or add small weights again and again until the rotor spins glass smooth. A shaft thicker than your body, balanced down to grams. That's the level we're talking about. Now the two halves come together, and it's a tense moment. The rotor has to slide into the stator with a gap between them sometimes thinner than a coin. Cranes lower the rotor in slowly, millimeter by millimeter, because if it scrapes the copper on the way in, you've just wrecked weeks of work. End bells and bearings get bolted on to hold the shaft, cooling systems are fitted, and the whole machine is wired up. But the factory still doesn't trust it, so it goes to the test bed. They hook the finished motor up to power and spin it, watching the temperature, the vibration, the current, listening for anything wrong, pushing it under load to prove it delivers the full power it promised. Every reading gets logged, and only when it passes does this giant finally ship out to a steel mill, a mine, or a power plant. So next time you watch glowing steel get squeezed through a rolling mill, or a haul truck climb out of a pit with 400 tons of rock, remember the silent monster doing the work. Miles of hand-wound copper, a shaft thicker than a person, baked solid and balanced to grams. One of the most extreme machines humans have ever built, and almost nobody ever thinks about it. If this blew your mind even a little, subscribe to Made on Earth, because we take you inside the machines that quietly run our world. And go watch how they forge a 300-ton steel shaft next. Trust me, you're not ready for that one. Somewhere in Buffalo, New York, sits a building so big it has its own weather. 3.1 million square feet of steel and concrete, the single largest engine plant on the planet.
General Motors set to make a major investment at its propulsion plant in the town of Tonawanda. $888 million will be used to install new machinery, equipment, and tools, along with other renovations there.
And inside, on a good day, a finished V8 engine rolls off the line every 10 seconds. 8,500 of them in a single day. Since this place first opened, it has built more than 63 million engines. Stack that up, and you've powered most of a century of American muscle. But here's the part nobody tells you. To turn a puddle of molten metal into 8 cylinders that fire 24,000 times a minute, this factory has to pull off something that sounds impossible. Stick around, because the way they do it is wilder than anything under your hood. Let's start with the scale, because the numbers are genuinely hard to believe. This one plant builds roughly 35% of every engine the company makes worldwide. 5 assembly lines run at once. At full tilt, that's a complete running V8 every 10 seconds, more than 8,000 a day. Think about that. In the time it takes you to read this sentence, 3 more engines just got finished. Now, a modern V8 isn't one part. It's around 1,000 separate pieces, each machined to a tolerance you can't even see, all coming together in a few hours. And it all begins with metal so hot it glows like the sun. Because before you can build an engine, you have to pour one. It starts with the block. The block is the skeleton of the entire engine, the giant chunk of metal that holds the cylinders, the crankshaft, everything. And most modern V8 blocks are cast from aluminum. In the foundry, solid aluminum gets dropped into a furnace and heated to around 700 degrees Celsius. That's 1300 Fahrenheit. Until it turns into a glowing silver liquid. For comparison, aluminum melts at 660 degrees, so they're pushing it well past the point of no return. Then comes the pour. Workers guide that molten metal into a sand mold shaped exactly like an engine block, hollow channels and all. Inside, cast iron sleeves are often locked in place, the surfaces the pistons will ride against. The metal floods in and cools. A few minutes later, they break the mold apart, and there it is. A raw engine block, born from a bucket of liquid metal. But it's nowhere near ready. Right now, it's accurate to about the width of your finger, and an engine needs to be accurate to the width of a hair. This is where the factory turns into a surgeon. The rough block gets clamped into a CNC machine, a computer-controlled cutting station the size of a small room. Spinning tools come down and shave the metal, drilling the cylinder bores, cutting the bolt holes, flattening the deck where the head will sit. And the precision here is almost absurd. The cylinder surfaces are machined to within a few microns. To put that in perspective, a single human hair is about 70 microns thick. These tolerances are 5 to 10 microns. That's roughly 1/14 of a hair. Cut too much, the engine leaks power. Cut too little, the piston seizes. So every block is measured, scanned, and logged before it's allowed to move on. One factory, building thousands a day, and each one held to a standard you'd need a microscope to check. Now for the heart of the whole machine, the crankshaft. This is the long steel bar that turns the up and down punch of the pistons into the spinning motion that drives your wheels. And it takes a beating like nothing else in the car. So they don't just cut it from a block, they forge it. A glowing hot steel billet gets slammed under a massive press, hammered into the rough crankshaft shape under thousands of tons of force. Forging packs the metal's grain tight, making it far stronger than a cast part. Then it goes to the machines, where the bearing journals, the surfaces that spin inside the engine, are ground down to between 5 and 10 microns. After that, it's spun and balanced, because a crankshaft turning thousands of times a minute that's even slightly off will shake an engine to pieces. One unbalanced gram, multiplied by all that speed, becomes a hammer blow. Get it perfect, and it spins smooth for 200,000 miles. With the block machined and the crankshaft ready, assembly begins. And this is where 1,000 parts start fitting together like a puzzle. The crankshaft drops into the bottom of the block. Then come the pistons, 8 of them, connected to the crank by steel rods. Each piston has to slide into its cylinder with a clearance thinner than a sheet of paper, tight enough to seal the explosion, loose enough to move at the speed of a bullet. On top goes the cylinder head, packed with valves, springs, and camshafts that open and close in perfect time, hundreds of times a second. And here's the wild part. On these modern lines, almost nothing is guessed. Every single bolt is tightened by a smart tool that records the exact torque and feeds it into a database. Every block carries a barcode, and the system tracks every step. If a worker skips one, the line refuses to move forward. The engine literally won't let itself be built wrong. Watch the line and it almost looks alive. Robotic arms swing oil pans and timing covers into place. Fuel rails, sensors, and miles of wiring get threaded around the block. Because a modern V8 is as much a computer as it is a machine, stuffed with sensors reading temperature, pressure, and the position of the crankshaft hundreds of times a second. Spark plugs go in, the intake manifold caps it off. And piece by piece, that rough chunk of cast aluminum from the foundry has become a complete, intricate, 1,000-part machine. But the factory still doesn't trust it. Not yet. Because a V8 that looks perfect can still hide a flaw you'd never see with your eyes. And the only way to find it is to make the engine come to life. So before this engine ever touches a car, it gets tested. First comes the cold test. The engine is hooked to a machine that spins the crankshaft electrically, turning it over without ever firing a single spark. Sensors listen to everything. Compression in each cylinder, oil pressure, the faintest leak, vibrations far too small for a human to feel. In seconds, the computer knows if anything is even slightly off. Some engines go further, onto a hot test, where they're actually fired up and run, roaring to life on a stand, and pushed under load to make sure they deliver the power they're supposed to. Every reading gets saved against that engine's barcode, forever. If it fails by even a hair, it's pulled. Only the ones that pass, flawless, get sent out the door to drop into a real car. And this is the payoff for all that obsession. A finished V8, like the 6.2-liter monster these plants build, makes nearly 500 horsepower. Supercharge it, and you're past 750. At 6,000 revolutions per minute, those 8 cylinders are firing 24,000 controlled explosions every single minute. That's 400 tiny, contained detonations every second, all perfectly timed by parts machined to a fraction of a hair, balanced to a single gram. Now, compare that to the other end of the spectrum. At Mercedes-AMG, they go the opposite way. One master technician builds an entire V8 by hand, start to finish, in 4 to 5 hours, then signs his name to a badge bolted right onto it. One engine, one human, one signature. 2 completely different philosophies, the factory that builds one every 10 seconds, and the craftsman who builds one a day. both chasing the same impossible perfection. So the next time you hear a V8 rumble at a stoplight, remember what it actually took. A puddle of metal heated past 1300 degrees, a block carved to a fraction of a hair, a crankshaft forged under thousands of tons and balanced to a single gram, 1,000 parts, every bolt logged, every engine tested before it ever turned a wheel, pouring out of the largest engine plant on Earth at a rate of 1 every 10 seconds. It's one of the most extreme manufacturing feats humans have ever pulled off, hiding in plain sight under a hood. If this blew your mind even a little, subscribe to Made on Earth, because we take you inside the machines and factories that quietly run our world. And go watch how the Gigapress casts an entire car body in 80 seconds next. Trust me, you're not ready for that one.
Stand beside the world's largest diesel engine. It towers 44 feet tall, higher than a 4-story building, stretches 89 feet long, longer than a semi-truck with trailer. 14 cylinders, each wider than oil drum, fire in sequence, producing 109,000 horsepower. That's the power of 1,600 cars concentrated in one single machine. This engine burns 250 tons of fuel daily, moving 20,000 containers across oceans at 23 knots. How does metal combusting heavy fuel oil generate force pushing 90,000-ton ships through water? Why build engines this enormous when smaller multiples could work? Stay with us. You'll discover the brutal elegance of two-stroke combustion at massive scale, and the shocking secret of why these engines burn fuel refineries consider waste. The cheapest, dirtiest.
Our journey begins at Hyundai Heavy Industries in Ulsan, South Korea, the shipyard building these mechanical titans. The engine manufacturing hall spans 30 acres under single roof. Overhead cranes rated at 600 tons glide on rails, positioning cylinder blocks weighing as much as locomotives. Workers look like ants beside components. Watch the cylinder casting. Molten iron pours into sand molds, creating a single cylinder liner. Hollow tubes where pistons travel. Each liner stands 12 feet tall, walls 4 inches thick. The iron must cool for 72 hours. Rush it, thermal stresses create microscopic cracks that propagate under operation, causing catastrophic failure. We make engines that run 30 years continuously, explains Chief Engineer. No second chances if casting fails.
The crankshaft arrives on specialized trucks, a single forged steel shaft weighing 300 tons, machined to tolerances measured in thousands of inches across 70-foot length. Installing it requires choreographed precision. Hydraulic jacks lift the shaft while technicians align bearing surfaces. One misalignment of ½ inch causes bearing failure within weeks of operation. Picture the assembly floor. 14 cylinder liners bolt to engine block, itself a 40-foot steel casting, forming engine skeleton. Each connection uses bolts diameter of baseball bats, torqued to specifications requiring pneumatic impact wrenches lasting 5 minutes per bolt. Assembly takes 6 months, 12-hour shifts, teams of 50 engineers and technicians. One finished engine represents 200,000 man-hours, equivalent of one person working full-time for 96 years straight.
The pistons dwarf automobile engines. Each piston assembly, piston, rings, and connecting rod weighs 6 tons. That's heavier than full-sized pickup truck. The piston crown, exposed to combustion, endures temperatures exceeding 1,800 degrees and pressures reaching 2,000 psi. Material science pushes limits here. Watch piston installation. Cranes lower assemblies through cylinder tops. Workers guide them onto connecting rod bearings with millimeter precision. The piston rings, spring steel bands sealing combustion pressure, get installed by hand. Each ring expands under tension, slip during installation, and the ring snaps, injuring workers and destroying components worth $50,000. Veterans develop feel for tension, installing rings quickly yet carefully. 20 years I've installed 3,000 pistons, says one assembler. Still respect every one.
Now grasp two-stroke operation. Elegantly simple, yet counterintuitive. Unlike car engines firing every other rotation, marine diesels fire every rotation. As piston descends, it uncovers ports in cylinder wall. Compressed air rushes in, pushing exhaust out simultaneously. The piston rises, compressing fresh air. Near top, injectors spray heavy fuel oil. Compression heat, not spark plugs, ignites fuel. Explosion drives piston down. The cycle repeats. This two-stroke design eliminates valves entirely. No camshafts, no timing chains. Fewer parts mean greater reliability. But it demands supercharging. Turbocharges forcing air into cylinders at 22 psi. Without pressurization, the engine wouldn't breathe. Turbochargers the size of sedans spin at 20,000 RPM, driven by exhaust gas. They glow red-hot during operation, requiring water cooling systems circulating thousands of gallons hourly. Fuel injection happens at extreme precision. Each cylinder consumes 16 gallons per combustion cycle, enough to fill your car's tank every few seconds. Injectors spray fuel as fine mist under 6,000 psi pressure. The atomization must be perfect. Droplets too large won't burn completely, wasting fuel. Too fine, combustion becomes explosive rather than controlled, damaging engine. The fuel itself surprises people. These engines burn heavy fuel oil, basically petroleum refinery leftovers after extracting gasoline, diesel, and jet fuel. It's thick as molasses at room temperature, must be heated to 240 degrees before flowing. Contains sulfur, metals, and contaminants that would destroy car engines instantly. But marine diesels tolerate it because economics dictate everything. Heavy fuel costs 40% less than automotive diesel. At 250 tons daily, that price difference means millions saved annually per ship.
Engine control happens from bridge via computer systems monitoring 600 parameters simultaneously. Engineers track cylinder temperatures, bearing pressures, fuel consumption, turbocharger speeds. The engine room, 3 decks tall, deafeningly loud despite ear protection, houses the mechanical orchestra. Walk the engine room during operation. Heat radiates from every surface. Metal creaks and groans as thermal expansion moves components fractions of inches. Across a 70-foot engine, that's feet of total movement. The crankshaft, visible through inspection ports, spins at 102 RPM. Seems slow until you realize this massive shaft accelerates tons of metal from 0 to maximum speed every single rotation. The forces involved bend physics. One chief engineer describes it, "This isn't machinery, it's controlled violence. We're detonating tons of fuel hourly inside metal box, converting explosions into rotation." Maintenance happens at sea on schedules measured in years. Every 8,000 hours, roughly 1 year of operation, crews perform major service. They drain lubricating oil, 60,000 gallons per engine, replacing filters the size of trash cans. Inspect cylinder liners for wear using ultrasonic equipment. Pull pistons for ring replacement. The most dramatic maintenance involves crankshaft inspection. Engineers use magnetic particle testing, apply magnetic field, spray iron particles, look for cracks where particles accumulate. Finding cracks in 300-ton crankshaft spinning at 100 RPM means potential catastrophic failure. The process takes 4 days of continuous work while ship sits idle, losing $200,000 daily in lost revenue. But catching cracks before failure saves the engine worth $15 million. No shortcuts exist. We maintain like lives depend on it, states chief engineer, because they do.
Rudolf Diesel invented compression ignition engines in 1897, demonstrating fuel efficiency double that of gasoline engines. His original design ran on peanut oil. Diesel envisioned farmers powering equipment from crop byproducts. The petroleum industry hijacked his invention, optimizing for their cheapest product, heavy fuel oil. Marine applications began in 1920s. By 50s, diesel surpassed steam turbines. The two-stroke design, perfected by Sulzer and Wärtsilä through 70s and 80s, became dominant. Today's largest, the Wärtsilä-Sulzer RTA96C, produces power exceeding small city power plant. Just 14 cylinders generating 109,000 horsepower. 23,000 containers moved by single engine. 98% of ocean cargo moves via diesel-powered ships. These engines literally keep global economy flowing.
Carbon emissions seem paradoxical. These engines burn dirtiest fuel, yet achieve 48% thermal efficiency, converting nearly half consumed energy into motion. Modern cars manage 25%. The efficiency comes from slow operation and massive scale, allowing effective heat recovery through turbochargers and economizers. Here's the secret we promised. Marine diesels burn fuel refineries would otherwise struggle disposing. That heavy fuel oil, thick, contaminated, full of sulfur, represents petroleum industry's bottom-of-barrel waste. Refineries initially paid ships to remove it. Marine engines transformed waste into commodity. Today, heavy fuel powers 90% of ocean shipping. Those engines burning waste move 60 billion tons of cargo annually, generating 3% of global carbon emissions, while handling 90% of international trade. From refinery waste to global commerce, the cycle completes. We've built machines so large they boggle comprehension, burning fuel so crude it seems impossible, moving cargo quantities that dwarf imagination. That container ship Horizon, powered by controlled explosions in cylinders taller than you, spinning crankshafts heavier than your house, burning fuel thicker than syrup. Engineering at scale where normal physics seems inadequate, yet it works reliably, efficiently, endlessly. These aren't just engines, they're the beating hearts of globalization itself.
Under the hood of your car, there's a part the size of a fist, spinning at 200,000 revolutions per minute, in heat like a furnace, at speeds close to a jet engine. You've never seen it, and you won't, unless you tear apart the engine. Think horsepower is all about engine displacement? Wrong. And you'll never understand what's really pushing you forward during that pass. Now here's the weird part. Metal melted at 2,500 degrees, flowing like lava. And within weeks, this part is born from it, precise down to the thickness of a human hair. How? I'm about to show you. It all starts with a special heat-resistant alloy. Regular steel won't cut it here. Exhaust gases from diesel trucks and powerful vehicles can heat a turbine to temperatures where many metals start losing their strength. That's why they use complex nickel alloys with chromium, cobalt, and other elements added in. The alloy is melted in furnaces at temperatures over 2,500 degrees Fahrenheit. Inside the furnace, the metal glows bright orange and looks like liquid lava. Even a tiny impurity or air bubble can turn into a future crack. So quality control here is literally total. Next comes one of the most critical stages, casting. The molten metal isn't poured into an ordinary mold, but into special ceramic shells. The future turbine blades have a complex curved shape. They must catch the exhaust gas flow as efficiently as possible while simultaneously withstanding enormous loads. The superheated metal, heated to over 2,500 degrees Fahrenheit, is prepared for pouring into the molds. But these aren't ordinary metal molds used for simple parts. The future turbine is cast in a special ceramic shell created specifically for a single product. First, they make a wax model of the turbine wheel. It already has all the future blades, curves, and channels. Then, they dip this model repeatedly into liquid ceramic slurry and coat it with fine sand. Layer by layer, a thick, hard shell builds up around the wax. When it dries, they melt out the wax, leaving behind a hollow mold accurate to within nearly a human hair. It's into this ceramic shell that they pour molten metal. The process looks stunning. Orange liquid flows through narrow channels and fills every curve of the future blades. And their shape is far from simple. If you look closely, they resemble twisted wings. This geometry is needed to capture the exhaust gas flow as efficiently as possible. After pouring, the metal slowly solidifies. Some facilities use controlled crystallization technology. Engineers literally control how crystals grow inside the metal. The reason's simple. A properly formed structure handles heat and vibration way better. Once the blank cools down, they destroy the ceramic shell. And here, for the first time, the future turbine appears, though right now it looks pretty rough. The surface is coarse and the geometry is still far from final. The next shop feels like a jewelry workshop for giants. Blanks get mounted into high-precision machines. Each blade is machined individually. Tolerances are measured in thousandths of an inch. If a blade's even slightly thicker or thinner than spec, the rotor balance gets thrown off. After casting, the turbine only vaguely resembles the finished product. Next comes the stage where the metal blank is refined to near perfection. I walk into the machining shop and everything looks like someone scaled up a jewelry workshop to factory size. Each turbine is secured in a high-precision machine. A computer controls dozens of cutting tool movements, gradually removing excess metal. It does this very carefully. In a single pass, the cutter can remove a layer thinner than a human hair. The blades get the most attention. They're the ones that take the hit from the hot exhaust gas stream. Every blade has the same shape, the same angle, and the same thickness. The machine moves between them with precision measured in thousandths of an inch. From the outside, it looks like a few thousandths of an inch difference between blades doesn't matter. But when the finished turbine starts spinning at over 200,000 revolutions per minute, even that tiny detail becomes a serious problem. An extra bit of metal creates imbalance. The rotor starts vibrating, bearing loads shoot up, and the entire assembly's lifespan drops. So after every machining stage, the part gets checked with measuring instruments. Laser scanners create a digital model of the turbine and compare it to the drawing. If even one blade falls outside tolerance, the part goes back for rework or gets scrapped entirely. This is where a rough casting transforms into a high-precision component that'll eventually withstand extreme temperatures, massive loads, and billions of rotations over its lifetime. After machining, the parts go through heat treatment. They're heated up and cooled down again, following a strictly defined schedule. This helps remove internal stresses that built up during casting and machining. But even after this, the turbine still isn't ready. Next up, quality control. And this is where it becomes clear why these parts cost so much. Every turbine gets checked for hidden defects. They use X-ray equipment for this. The metal literally gets scanned all the way through. Operators look for microscopic voids, cracks, or foreign inclusions. After the X-ray comes balancing. This is one of the most fascinating processes at the factory. The turbine is mounted on a specialized test stand and spun up to speeds that are almost impossible to imagine. For some models, that's over 200,000 revolutions per minute. Even an extra gram of metal at that speed becomes a serious problem. A computer detects the slightest imbalance, after which the operator removes a microscopic amount of material at precisely the right spot. Then the procedure repeats again and again until the parameters are perfect. And only now does the turbine make it to the turbocharger assembly. Here it's mated with the compressor wheel and shaft. In the finished unit, exhaust gases spin the turbine, which drives the compressor through a common shaft. The compressor pumps more air into the engine, and more air means more power without increasing engine size. That's why modern passenger cars increasingly use small turbocharged engines instead of large, naturally aspirated ones. And in the world of trucks, turbochargers became practically mandatory a long time ago. The scale of production is staggering. Major factories can churn out hundreds of thousands of turbos a year. Each one goes through dozens of inspections. From the moment metal melts to the finished part can take weeks. The funny thing is, drivers almost never see the result of all this work. The turbo hides deep under the hood. It doesn't gleam with chrome or turn heads in a parking lot. But this one small component often determines whether an engine has enough power to pass, climb uphill, or haul tons of cargo clear across the continent. And when you look at the entire process, from glowing hot metal to a finished rotor, you start to understand why turbine manufacturing remains one of the most complex branches of modern engineering. It's not enough to just cast a chunk of metal into the right shape. You need to create a component that will operate for years in an environment where the temperature resembles a furnace and the rotational speed approaches that of jet engines. And all of this so that every press of the gas pedal feels exactly the way the engineers intended. And to make sure you don't lose track of my channel, you should subscribe to it. Did you do it?
Every year, massive ship engines are built as tall as a 4-story building, and spinning at their very core is a shaft weighing up to 300 tons. That's more than a passenger jet. But how is this steel backbone born? One capable of handling millions of pound-feet of torque and running non-stop for 30 years? Why can't you just cast it? And what engineering magic does the shrink-fit method hide? In this video, you'll see fire, liquid nitrogen, and pressures in the tens of thousands of tons. And if you stick around to the end, you'll discover the secret that makes this giant practically immortal. The birth of this steel backbone doesn't start in an assembly shop. It starts in massive forges where metal gets tamed by fire and crushing pressure. Unlike small car crankshafts, you can't cast something this big in one solid piece. It would just crack under its own weight. A crankshaft at this scale is built from separate forged components, then joined into one single unit. The shop air is thick with hot metal and oil, and the floor shakes with every machine movement. It all begins with steel ingots weighing dozens of tons. These colossal blocks of metal, like clumsy gray boulders, get loaded into furnaces the size of a small house. For many hours, sometimes even days, the steel soaks up heat until its temperature climbs past 4,000 degrees Fahrenheit. When those heavy furnace doors finally swing open, the shop floods with blinding yellow-hot light that hurts to look at. The metal doesn't look solid anymore. It glows from within, radiating heat so intense that even 30 feet away, your skin starts to burn. Now the massive manipulators enter the game, carefully but confidently grabbing the white-hot ingot and transferring it to the press. This press is a god of forging. It's not just big, it's colossal. When those hydraulic cylinders start moving, you hear a low rumble that passes through your entire body. The pressure it generates reaches an incredible tens of thousands of tons. Before your eyes, something unbelievable happens. Under the blows of this monster, the steel ingot starts changing shape like it's made not of metal but of soft Play-Doh. Each strike comes with a thunderous sound and clouds of scale flying in every direction like fiery rain. This is how, step by step, the press shapes the throws. These are the bends, or knees of the shaft, which are its most critical parts. Every single piece has to be forged with surgical precision, because these crankshafts will eventually take the punishing blows of the pistons. And the pistons in this engine? By volume, they could rival a small bedroom. Each downward stroke of the piston, that's the energy of exploding fuel converting into rotational motion of the shaft. Watching this process, you realize no casting could ever give the metal this kind of internal strength. Forging under massive pressure compacts the steel's structure, making it virtually immune to fatigue and cracking. This is the birth of a true titan, one that'll carry the might of an entire ocean liner. After the giant press finishes its work, the steel still isn't ready for duty. Right now, it's in a state of internal stress, and if you just let it cool in the air, it'll become brittle. That's why the heat treatment stage comes next, and it demands iron patience. These steel blanks have to be heat-treated in special baths and furnaces, where the metal is slowly heated and cooled on a strict schedule. This changes the internal structure of the crystal lattice, making it tough and incredibly strong. Only then can the crankshaft withstand the insane loads for the next 30 years of continuous operation in the ocean. But the real engineering puzzle lies elsewhere. How do you transform separate forged parts into a single monolith capable of withstanding torque in the millions of pound-feet? The answer lies in the magic of physics, called the shrink-fit method, or interference fit. It's a spectacle that makes even experienced craftsmen hold their breath. Picture this. The central sections of the shaft, massive steel cylinders, are plunged into baths of liquid nitrogen. The temperature there drops to minus 321 degrees Fahrenheit. Metal reacts to this extreme cold predictably. It starts to contract. The shrinkage is microscopic, literally hundredths of an inch, but for precision engineering, that's enough. While the shafts cool down, the outer components, massive crankshaft cheeks, get sent to heating furnaces. Under the heat's influence, the holes in these cheeks expand. When both parts reach the required temperatures, the critical operation begins. Using a crane, the chilled central section is quickly and precisely inserted into the expanded hole of the hot cheek. Workers have just minutes before the temperatures start to equalize. As soon as the metal begins taking on the shop's ambient temperature, something truly remarkable happens. The hot outer part contracts while the cold inner part expands. They grip each other with such colossal force that the boundary between them virtually disappears. The steel bonds at a molecular level. Tension builds up that'll hold these parts together forever. No bolt, stud, or cutting-edge weld in the world could deliver this kind of strength and reliability. This joint is impossible to break without destroying the metal itself. Once the shaft is assembled, it heads to a massive lathe. It's a sight you won't forget. A 300-ton steel beam, slowly rotating while ultra-powerful cutting tools shave off inches of metal, transforming the rough form into a perfectly smooth surface. At this stage, every inch of the surface gets checked by laser measuring devices. The machining precision on the shaft journals, where it'll sit in the bearings, has to be phenomenal. An error of just a few thousandths of an inch will cause friction during engine operation that'll literally incinerate the metal in minutes. Balancing deserves special attention. Picture an object weighing 300 tons that has to spin at over 100 revolutions per minute. If one side of the shaft is even a few pounds heavier than the other, it'll create vibrations so powerful they could rip apart the hull of a massive container ship like a cardboard box. Engineers use special computerized balancing machines to detect the tiniest imbalance. They drill out excess metal in specific spots or add special weights until the shaft spins perfectly true. When balancing is complete, this giant becomes so balanced that you could literally get it spinning with just a few people pushing. The final stage is polishing. The surfaces that'll contact the bearings get a mirror finish. This is done so that the oil film, delivered under insane pressure, perfectly separates the steel shaft from the bearing's babbitt metal. Essentially, this 300-ton monster will literally float on the thinnest layer of lubricant during operation, never directly touching the bearing metal. It's a true triumph of engineering over friction and weight. Now this finished crankshaft gets loaded onto special platforms and hauled to where they assemble the engine itself. When you're staring at a completed powerhouse that stands 44 feet tall, that's like a 4-story building, you realize this shaft is its backbone. All the power that pushes a vessel the length of 4 football fields across the ocean runs through it. For the next 20 to 30 years, it'll spin non-stop, covering thousands of miles, moving goods all around the world. It's incredible, but every single one of these shafts is a custom product. They're not churned out on an assembly line. Each one has its own passport, its own story of casting and machining. Looking at a machine like this, you understand that humanity can tame any force of nature if you throw enough knowledge and steel at it. This was a real journey into the world of giants, and I hope you felt that energy hidden inside these tons of perfectly machined metal. So here's my question for you. Do you think there's a limit to how big these engines can get? Or have we already hit peak steel evolution? Drop your thoughts in the comments. I'm genuinely curious to hear what you think. Smash that like button if these massive scales blow your mind too, and subscribe because we've got plenty more objects coming up where size absolutely matters. Every year, new power plants fire up around the world, lighting up entire megacities. But their safety hinges on a single component. Picture a steel ingot heated to 2,200 degrees Fahrenheit, weighing 300 tons, getting slammed with the deafening roar of a force equal to 15 Eiffel Towers. Why subject metal to this hellish torture under a 50,000-ton press? Stick around till the end, and you'll discover engineers' biggest secret: how a tiny invisible air bubble the size of a pea can tear apart a $5 million turbine. You'll witness the shocking process of healing steel that keeps these massive machines spinning for 60 years without a single crack. Ready to feel that heat through your screen? Let's go. Look at this. Hanging in front of us is a glowing steel ingot about 13 feet long and 6 feet in diameter. It weighs 300 tons and glows bright orange. This beast tops out at 2,200 degrees Fahrenheit. It's so hot that from 50 feet away I can feel the inferno on my face, even though I'm standing behind a protective screen. The ingot hangs on massive chains, each link as thick as my leg. Why can't turbine shafts just be cast in a mold like regular parts? The answer's simple: pores and microcracks. When you pour molten steel into a mold, air bubbles the size of a pea or even a fist get trapped inside. You can't see them at first glance, but when the shaft starts spinning under loads of several thousand tons, these weak spots start to fail. After a year or two, the shaft can crack, and that's catastrophic for the entire power plant. So the only way is forging, which compresses the metal and closes all the defects. This ingot was poured at the steel mill 3 days ago. First, they melted over 300 tons of steel in an electric arc furnace at temperatures reaching 3,000 degrees Fahrenheit. Then they cleaned this molten metal of impurities in a vacuum chamber, a process called vacuum degassing. If too much water or oxygen stays in the steel, the metal becomes brittle. After cleaning, they poured the melt into a massive mold and left it to cool for a week. What you get is a cylindrical ingot called an ingot. But a freshly cooled ingot isn't a finished part yet. Inside the metal, there's an uneven crystalline structure, residual stresses, and micro defects. Forging solves all these problems at once. Watch what's happening now. They're lifting it from the preheating furnace where it's been heating for the last 12 hours so the temperature is uniform throughout the entire volume. A hydraulic forging press looms above us. This is the biggest press in this plant with a 50,000-ton capacity. For comparison, that's like stacking 15 Eiffel Towers on top of each other and letting them drop on this chunk of metal. The press consists of 4 massive columns, each 5 feet in diameter, and an upper crossbeam that weighs 200 tons all by itself. Right now, the operators are firing up the manipulator, giant mechanical arms that can rotate the ingot in any direction. The manipulator is controlled from a cabin where the smith sits, but this isn't the hammer-swinging smith you've seen in the movies. This is a highly skilled engineer who runs the entire process using joysticks and computer systems. He watches screens that show the temperature of every section of the ingot in real time through infrared cameras. From the start, the press drops and hammers the ingot with 15,000 tons of force. The sound is so loud that even through earplugs I feel the vibration in my chest. The ground beneath my feet shakes. The ingot flattens slightly, maybe 2 inches per strike. But this isn't just brute force. Every blow has to be precisely calculated. Hit too hard in one spot, the metal can crack. Too soft, the structure won't compress. The manipulator rotates the ingot a quarter turn, and the press strikes again. Then another rotation, another strike. This is called radial forging. The ingot is worked evenly from all sides. About 5 strikes happen per minute. Each strike sends out a fountain of sparks and flying scale. That's the oxidized layer of metal that cracks and flies off under pressure. Why does all this need to happen so fast? Because the ingot is cooling. Below 1900 degrees Fahrenheit, the steel becomes too hard to forge, and it won't deform, it'll crack under the press strikes. So the blacksmith has just about 45 minutes to complete the first stage of forging while the metal's hot. Miss that window, and you're sending it back to the furnace for another 12 hours of heating. That's lost time and money. Watch how the ingot's shape transforms, from a thick cylinder into a longer, thinner bar. This is called drawing out. The blacksmith controls the manipulator to press a bit further from the center with each strike, gradually stretching the metal. Over a year of forging, the ingot's length increases from 3 feet to 45 feet, while the diameter shrinks from 6 feet to 4.5 feet. Under the press's pressure, the steel's crystalline structure reorganizes. Large grains break down into smaller ones, micro cracks close up, pores flatten and weld shut. It's like healing a wound. Under pressure, the defect's edges fuse together, and the metal becomes solid. After forging, the steel becomes 20 to 30% stronger than cast metal. After the first forging stage, the ingot goes back into the furnace, but this time for normalization. The temperature maxes out at 1650 degrees Fahrenheit. The ingot sits at that temperature for 10 hours. This lets the steel rest. Internal stresses that built up during forging get distributed evenly, and the structure becomes uniform. Then the second forging stage begins. This time, the blacksmith works on the details, shaping the shaft's specific profile, forging the future bearing locations, creating transition zones. The press hits with less force, now 8,000 tons instead of 15, but with greater precision. Every strike is planned using a 3-dimensional computer model. Interestingly, during forging, the ingot loses weight. Some of the metal turns into scale, an oxidized layer that flies off under the strikes. Over the entire manufacturing process, the loss comes to about 5% of the starting weight. That's 15 tons of metal that just turn into rust and flake away. But it's a necessary sacrifice for quality. After the second forging stage, the shaft undergoes heat treatment, normalization, and tempering. It's heated to 1600 degrees, then freely cooled at a rate of 50 degrees Fahrenheit per hour. The entire cycle takes about 5 days. This slow heat treatment relieves all residual stresses and ensures stable mechanical properties along the entire length of the shaft. Next comes machining. The shaft is mounted on a giant lathe 70 feet long. Tungsten carbide cutting tools turn it, removing about 2 inches of surface metal along the entire length. This removes the layer with surface defects and brings the diameter to precise dimensions within 5/1000ths of an inch. The most critical moment is quality control. Each shaft undergoes ultrasonic defect testing. Special sensors send ultrasonic waves through the metal's thickness and listen for echoes. If there's a void or crack inside bigger than 1/8 of an inch, the sensor will find it. Also perform magnetic particle inspection of the surface, which can detect a crack less than 1/100th of an inch deep. The cost of a single shaft like this anywhere from $2 to $5 million depending on size and specs. But the service life, 40 to 60 years of continuous operation, spinning at 1800 revolutions per minute, transmitting power of about 1,000,000 kilowatts. Over 60 years, that's billions of rotations under colossal loads. The entire production cycle of the shaft, from melting the ingot to the finished part, takes about 6 months. Forging is just one stage, but a crucial one. It's the forging that transforms an ordinary steel ingot into a component capable of working for decades under the most brutal conditions. Thanks for being with me in this incredible forge. If you enjoyed this, hit that like button and subscribe to the channel. Next time, we'll head to a nuclear power plant and see how these shafts get installed and started up. See you then! Millions of tons of steel get forged worldwide every year, but only a handful become true mechanical titans. Picture a part weighing 30 tons. That's like 10 adult elephants compressed into a single ring. Here's the paradox. This behemoth must be machined to within a micron, thinner than a human hair. One of these bearings costs up to $3 million, and if it fails, the losses hit tens of millions. How do you make a steel monster perform with Swiss watch precision under thousands of tons of pressure? Stick around till the end, and I'll reveal the secret engineers keep hidden. What actually happens to metal when it gets shocked in oil? And why, without one critical step, this 30-ton beast will shatter like glass? You've never looked at metal this way before. I'm standing right now next to what will become a bearing for a tunnel boring machine shield. This is a steel ring 26 feet in diameter, weighing around 30 tons. And here's the most amazing part. This massive thing needs to be machined to within 0.002 of an inch. That's thinner than a human hair. Let's start from the very beginning, with material selection. For bearings like these, they choose special alloy steel or similar alloys. This steel contains chromium, molybdenum, and other alloying elements that make it super strong and wear-resistant. Interesting fact, Chinese engineers developed an improved version of this steel specifically for 26-foot bearings, the largest in the world. The first stage of production is forging. Steel blanks are heated to 2,000 degrees Fahrenheit and forged under massive presses applying thousands of tons of force. The forging process aligns the metal's grain structure, making it stronger and more uniform. Here's a press as tall as a 3-story building that came down on red-hot steel with enough force to flatten a bus. After forging comes rough turning, enormous lathes, some the size of a 2-car garage, machine the blank, shaping it into a ring. The cutting tools for these lathes are made from tungsten carbide, a material 10 times harder than regular steel. Even so, these cutters wear out after just a few hours of work. Now for the crucial stage, heat treatment. This is what transforms ordinary steel into a nearly eternal material. The bearing ring is loaded into a giant furnace and heated to temperatures between 1550 and 1650 degrees Fahrenheit. At this temperature, the crystal structure stabilizes, ready for the next shock. Then comes quenching, the most dramatic moment in a bearing's life. The red-hot ring gets rapidly cooled by plunging it into an oil bath. The temp drops from 1600 to 300 degrees Fahrenheit in a matter of minutes. The oil hisses, boils, creating clouds of vapor. This sharp temperature shock transforms the steel's internal structure into martensite, a super hard crystalline form. But hardened steel has a problem. It's brittle as glass. One hit, and the multi-ton ring could crack. That's why the next step is tempering. The bearing gets heated again, but this time only to 350 to 500 degrees Fahrenheit. It's held at that temperature for 4 to 8 hours, then slowly cooled. Tempering reduces internal stress, makes the steel less brittle, but keeps the hardness. After heat treatment, the bearing has to go through rigorous inspection. They use ultrasonic equipment that can find an internal crack smaller than 8 inches. They also check microstructure samples. They take small pieces of metal and look at them under a microscope. You need 100% martensite with no retained austenite. Now begins the most precise stage, precision grinding. This is what separates a simple steel ring from a high-precision bearing. Look at this grinding machine. It's a specialized piece of equipment that costs several $1 million. The abrasive wheel spins at 5,000 revolutions per minute, removing microscopic layers of metal. Grinding happens in multiple stages. First comes rough grinding, which removes about 1/10 of an inch of material. Then finish grinding, which works to within 5 microns. Each pass of the grinding wheel is monitored by laser sensors that measure material thickness in real time. But that's not the end. After regular grinding comes super finishing, a process that makes the surface incredibly smooth. They use fine-grained abrasives and special techniques that reduce surface roughness to fractions of a micron. Under a microscope, this surface looks almost like a mirror. Why is this precision critical? Because these bearings operate under incredible loads. Take a tunnel boring machine, a beast that chews through solid rock. The cutting head, 57 feet in diameter, spins as it tears into granite. The force acting on the bearing reaches thousands of tons. If the bearing surfaces are uneven, even by a few thousandths of an inch, stress concentration zones appear. Metal at those points starts wearing down, heating up, and the bearing will fail. For large bearings, a segmented design is often necessary. A bearing over 30 feet in diameter can't be made in one piece. It simply won't fit in any heat treatment furnace. So they're made from separate segments, each machined individually, then all joined together with micron-level precision. The joints between segments must be so precise you can't even feel them with your finger. Interesting detail, for wind turbine bearings, they often grind a special profile called a crown. This isn't a decorative element. The crown distributes the load so maximum pressure falls on the center of the bearing, not the edge. If the load concentrates at the edges, premature wear occurs. The crown might be only a few thousand inches tall, but its shape is calculated by sophisticated computer programs. Let's talk about scale. One company, rotor, manufactured over 2,500 bearings for tunnel boring machines in 3 years of operation. Each one unique, engineered for a specific machine and geological conditions. The cost of a single bearing ranges from $500,000 to $3 million depending on size. Sounds like a lot? Now picture this. If a bearing fails deep inside a tunnel, repairs can cost tens of millions and halt construction for months. The service life of these bearings is measured in decades. A wind turbine bearing must run for at least 25 years, generating millions of rotations. A bearing for a tunnel boring shield can chew through 15 miles of solid rock, spinning day and night for 3 to 4 years. Quality control here is absolute. Every bearing gets checked on a coordinate measuring machine, accurate to 200 thousandths of an inch. It's a room-sized machine operating in a temperature-controlled room, plus or minus half a degree Fahrenheit. Why such precision with temperature? Because steel expands when heated. Temperature swing of just 2 degrees can change the bearing size by several thousandths of an inch, enough to ruin all measurements. They also run fatigue tests. They take metal samples from the very first batch and cyclically load them millions of times, simulating years of operation. If a sample fails before the calculated lifespan, the entire batch gets rejected. Harsh? Yes. But there's no other way. Billions of dollars in investments and human safety are on the line. The coolest thing about all this, the combination of gigantic size and incredible precision. It's like building a clockwork mechanism the size of a house. A part weighs a ton, but has to be accurate to within microns. A deviation you can't see with the naked eye can destroy the entire structure. And to keep my channel from falling apart, I'm counting on your comments and subscriptions. Subscribed? You sure you subscribed? And now? Alright then, let's continue. Engineers are constantly improving the technology. Right now they're testing new coatings for bearings, nanostructured films just a few microns thick that can double their lifespan. They're also developing sensors built right into the bearing that monitor temperature, vibration, and wear in real time. These smart bearings can warn you about a problem a month before it fails.
Your transmission is made up of 800 parts, and a single error of 1,000th of a millimeter on any of them means metal grinding instead of a smooth start. Most people think automatic is just convenient technology, but behind that quiet gear shift lies a manufacturing process where 1 degree of difference in a heat furnace ruins an entire batch of gears, where equipment costs as much as a house, and where one person is responsible for 1,000 parameters at once. I got inside one of these factories. I'll show you why these transmissions cost as much as real estate, and which one process even robots still can't replace. It all starts with the parts. Gears, shafts, clutches, valves, electronic modules. Each part arrives on its own schedule, sometimes from different countries. Picture a supply chain where every component is a tiny organism that has to play nice with the others. From the outside, the transmission looks compact, but inside, every element, each precise to within microns. For perspective, a micron is 1,000th of a millimeter, or roughly 1/50,000th of an inch. When they say micron-level precision, it's not a metaphor, it's the standard. Assembly has several zones. First up is machining. Shafts and gears get cut on mills and grinding machines. Here it's not just about getting the right shape. You need to hit the right surface hardness and tolerances. A gear with the wrong profile will rattle and overheat. Then, heat treatment. Parts get hardened, tempered, sometimes coated for special protection, wear reduction. When the material behaves differently, even 1.5 degrees difference in the furnace can shift the characteristics. So temperature control here is like monitoring a patient's pulse. Next up, clean rooms. No, not as sterile as an operating theater, but dust here is enemy number one. Where synchronizers and valves are involved, even a microscopic particle can trigger a jam. One reason these plants are rare, the need for expensive cleaning equipment, air filtration systems, special lines, special gloves and tools. Major investment. And that's why production concentrates in just a few places. Meanwhile, assembly runs parallel. Modern automatic transmissions aren't just mechanics, they're packed with lines of code and tiny control units. Electronics manage hydraulic pressure, gear engagement timing, and shift algorithms. Crucially, mechanics and electronics must play nice. Calibration after installation delivers that final chord of quality. If the electronics read wrong, the transmission will shift with a jerk or stick in one gear. It's both risk and scale. You're dealing with mechanics living in the real world and digital logic deciding in milliseconds. Main assembly. It's a blend of handwork and automated stations. The robots handle precision operations, pressing in bearings, torquing bolts to exact specifications, assembling modules using perfectly matched pairs. Humans do the detailed work, checking clearances, visually inspecting surfaces, performing operations that are tough to fully automate. Every transmission goes through testing on benches that simulate real-world conditions in a vehicle. Trial runs, heat cycles, load testing. On the test bench, a transmission runs for hours. They're checking shift feel, noise levels, fluid leaks. This is where hidden defects show up, things you'd never catch during assembly. If something's off, back it goes for disassembly and correction. Quality control? That's a whole different ballgame. They use instruments that measure shaft balance down to 1/10 of an ounce-inch, check surface roughness in microns, verify gears for profile accuracy. It's not cheap. The lab is basically a separate mini-factory with highly skilled personnel. Documentation is critical here. Every operation gets logged, parameters recorded. If a machine owner shows up a year later with a complaint, engineers can track down any part by serial number and check how it went through production. That's part of why these transmissions cost so much. Not just material costs, but the incredible level of control and tracking at every single stage. During the tour, they showed me one critical area, the grinding shop, where gears come out of the machines and head to final finishing. The smell of hot metal and oil hangs in the air, equipment hums, and at the same time, every operation is measured by laser scanners and ultrasound. They also do static shaft balancing in a clean room right there. An unstable shaft can cause vibration, and vibration at 10,000 RPM, that's a catastrophe. Tools lie on the floor next to the machine, but the master says, skill and experience matter more. Some things just can't be passed on through an algorithm alone. On the line, I watched dozens of parts come together to form a module. Several modules, and you've got a subassembly that then gets built into a housing. The transmission case sometimes weighs several dozen pounds and contains shafts, friction packs, planetary gears, and hydraulics. Planetary gears are their own kind of beautiful. Little satellites transferring torque, working in tight contact. If the clearance is even slightly off, the gear set whines and wears out fast. You need precision bearings here, and special fluid. The fluid formula matters. It handles pressure and heat, avoids foaming. Every little thing affects how long the transmission lasts. The risk in this business isn't just technical, it's economic. When you invest in a line, that's millions of dollars. One plant counts on thousands of transmissions a month, but the market can shift. A drop in demand or changes in vehicle standards can hit hard. Add geopolitics to that. Supplies of strategic materials, like high-grade steels or electronic components, can get stuck at customs. That's why not many companies take the risk of running the full production cycle. Toward the end of the tour, they let me peek into a back room with those same secret templates and tools. A few people are working on calibrating sensors, some scanning surfaces on a machine that costs as much as a house. One mistake, and an entire batch can go to waste. When a worker tells me 1,000 tiny parameters are riding on each task, I don't doubt it for a second. This is no place for carelessness. Walking back through the gates, I think about scale. Dozens of assemblies pass through this facility every single day, each one the result of years of development, engineering thought, and massive investment. You might not see these boxes while you're cruising down the highway, but when they leave this plant, they're a product of serious accountability. Next time you hear that quiet, tighter gear shift in your car, remember there are people and machines somewhere investing time and value to get it exactly right. When you look at this tangled maze of gears, channels, and valves, it becomes clear that assembling a transmission at the plant isn't some hobbyist's playground. It's a genuine test of nerves and high-precision equipment. Everything here hinges on fanatical attention to the tiniest details, because micron-level precision in manufacturing is the only law that cannot be broken without fatal consequences for the entire vehicle. If you've ever wondered how to build an automatic transmission, the answer lies in these 800 individual parts, each one needing to slot perfectly into place on the first try without any unnecessary friction. A lot of people ask why expensive transmissions cost as much as a small house in the suburbs, but just look at these tolerances. An error of 1/1000th of an inch instantly turns your smooth launch into a series of horrifying jolts and metallic grinding. The final bench testing of automatic transmissions is the moment of truth, where every hydraulic valve has to fire within milliseconds under 300 pounds per square inch of pressure, or else this entire iron brain will simply burn itself out from the inside within the first mile down the road. There are parts in cars nobody thinks about, until they break down in the middle of the highway at 3 in the morning with a fully loaded trailer. The axle and differential, those are exactly such parts. They hide under the frame, covered in dirt and grease, and over the entire service life of a truck, they might not get any attention except for an oil change once a year. But it's through them that torque passes from the engine to the wheel. On a heavy highway tractor, this torque can reach 5,000 pound-feet. For comparison, a sporty Porsche 911 puts out 350 to 400 pound-feet, and it's very powerful. In other words, through one rear truck axle passes loads 12 to 14 times greater. And this part cannot fail. At all. Ever. The plant where I'm at is Dana Incorporated in Fort Wayne, Indiana. They make axles and differentials for heavy-duty pickups like the Ford F250 and F350, for buses, for construction equipment, and for semi-trucks. Manufacturing axles and differentials for heavy machinery is a narrow specialty, and the serious players in this niche across all of North America you can count on one hand. The barrier to entry? Several $100,000 in equipment and years perfecting the technology. Most companies just buy finished axles instead of trying to make them in-house. We start with the axle housing, that same crosswise tube you see under the rear end of a pickup or truck. On light vehicles, it's stamped from sheet steel and welded together. On heavy ones, it's cast or forged. For rear axles, they cast the housing from ductile iron or steel in a sand mold. And one such casting, after machining, weighs anywhere from 120 to 280 pounds, depending on load capacity. A sand mold isn't what you think. It's not just holes in the sand. The mold is made from a special mixture of silica sand and resin, which gets packed into a metal box and baked in an oven. The accuracy of such a mold is plus or minus 60 thousandths per foot of length. Sounds rough, but for a casting that then goes to machining, it's plenty. After casting, the housing goes to the lathe and milling machine. The bearing seats are bored out. Threaded holes for the differential case mounting are cut with precision that guarantees uniform tension on all bolts during assembly. Then the housing goes to wash. A stream of cleaning solution at 80 pounds per square inch blasts out all the chips and sand left over from casting. If even one tiny chip stays inside and gets into the oil, it'll destroy a bearing at a few thousand miles, and nobody will figure out why. Now the main pair, the ring gear and pinion gear, this is where what separates serious axle manufacturing from everything else begins. These two gears transmit torque from the drive shaft to the differential and onto the wheels. Their teeth are cut at an angle. This is a hypoid pair, where the axes of the two gears don't intersect but pass each other in space. This exact geometry allows lowering the drive shaft and reducing the tunnel in the cabin, and it's precisely what creates a contact geometry that's simultaneously the zone of maximum load and maximum sliding, meaning the most hostile environment for any gear tooth. Ring gear blanks are forged from alloy steel, the traditional chromium, nickel, and molybdenum formula. A ring for a heavy-duty axle has an outer diameter between 14 and 22 inches, and weighs anywhere from 25 to 60 pounds. The forging goes to a lathe where they remove the black scale allowance, then to a gear hobbing machine. The spiral bevel tooth is cut by a cutter head that simultaneously rotates and moves along a complex spatial path. A single pass on one tooth takes 2 to 4 seconds. A ring gear for a heavy-duty axle has 38 to 48 teeth, and the entire cutting cycle runs about 3 to 4 minutes per part. After cutting comes heat treatment, carburizing in a carbon-rich gas atmosphere at 1700 degrees Fahrenheit for 4 to 8 hours. The tooth gains a hard, wear-resistant surface layer 35 to 60 thousandths of an inch thick, while keeping a tough core that absorbs impact loads without cracking. Grinding the teeth after hardening is the longest and most precise step. The grinding machine passes over each tooth and brings the final profile to within plus or minus 0.2 of a mil on tooth thickness. For parts transmitting 5,000 pound-feet at 1,000 RPM, this precision isn't overkill. It's exactly what's needed so the teeth contact across the proper area, not at the edge or center. Miss by 3 mils in the profile, and under load, the contact patch shifts and the tooth breaks on the very first loaded cycle. After grinding, they check a gear pair, the ring and pinion, together for a contact pattern. The gears are coated with a special paste, rolled under 5 to 10 pound-feet of load, and inspected to see where marks appear on the teeth. The pattern should be in the central zone of the tooth, not running to the edge, and it should have a specific shape, depending on the gear type. If the pattern's off, the pair goes back for adjustment or gets scrapped. A good inspector reads that pattern as confidently as a dentist reads an X-ray. The differential is a mechanism inside the axle housing that lets the left and right wheels spin at different speeds through turns and over uneven ground. For a heavy truck or bus, the differential carries extra loads. When one wheel's on ice and the other's on asphalt, the torque difference between them can hit 1,000 to 1,500 pound-feet. The differential case is, again, a ductile iron or steel casting with 4 or 6 spider gears inside. The spiders are small bevel gears, 1 to 2 inches in diameter, but their load per unit of tooth area is among the highest of any gear in the vehicle. They're also case-hardened, heat-treated, and ground. Axle assembly is a job that both robots and people do together at this plant. A robot installs the bearings into the housing with an interference fit of 1 to 2 mils, presses them in with 2,000 to 5,000 pounds of force. A human sets the adjusting nuts and dials in the preload on the main pair's bearings, a critical parameter that determines the service life of the entire axle. Too little preload and the bearings rattle and wear out in a few tens of thousands of miles. Too much and they overheat and fail in the same time frame. The window between too little and too much is 2 to 4 mils of axial play, measured with a dial indicator right there on the assembly stand. After assembly, each axle goes to a break-in test stand. It's spun for 10 to 20 minutes at various speeds and loads while measuring bearing temperature and noise levels. Noise is measured with a microphone in a soundproof chamber and compared against a reference spectrum. A characteristic howling sound, the so-called wolf frequency, indicates improper contact pattern or deviation in tooth profile. If the microphone picks it up, the axle gets disassembled and the cause is found. Because on the road, that sound will only get worse, and the problem won't just disappear on its own. At final inspection, samples from each batch are pulled and completely disassembled. Gear teeth are measured, bearings are removed and their condition checked after break-in, contact pattern is verified once more. If they find anything that shouldn't be there, the entire batch gets stopped and every axle is analyzed. Poor installation when mounting on the vehicle, or the wrong oil. The axles themselves? Rock solid. Because a part that's made this entire journey, from casting to the test stand, leaves the factory with enough margin to survive 1,000,000 miles under load. That's roughly the lifespan of a heavy-duty axle with proper maintenance. 1,000,000 miles. That's 20 trips around Earth's equator. Hit subscribe. The next facility is already queued up, and it's even more massive. Drop a comment with where you're from. Maybe next time I'll swing by your neck of the woods.
Every year, millions of semi-trucks hit American roads, and each one rides on 18 wheels. A wheel seems like just a wheel. But I'm standing here at the Alcoa plant in Cleveland, Ohio, and I can tell you, what happens to a chunk of aluminum in this place is one of the most spectacular shows in heavy industry I've ever seen. Let's start with a question most people never ask. Why aluminum in the first place? A truck is a machine that only makes money when it's moving. And every extra pound of its own weight, that's one less pound of cargo it can legally haul. In the US, the maximum gross vehicle weight for trucks on federal highways is 80,000 pounds. That's the law. So if the truck weighs more, it hauls less. And if it hauls less, it earns less. The math is simple. A steel wheel for a heavy-duty truck weighs about 40 pounds. A forged aluminum wheel, roughly 29 pounds. The difference? 11 pounds per wheel. Across 18 wheels, that's nearly 200 pounds. 200 pounds that can be converted into 200 pounds of additional cargo. Multiply that by hundreds of trips per year, and the difference in revenue becomes very real. That's why aluminum. But there's a catch. Aluminum is a soft metal. A truck wheel lives in conditions that would break most metals pretty quickly. Pounding from uneven roads, constant load from tens of thousands of pounds of cargo, heat from the brakes, temperature swings from -20 to over 100 degrees Fahrenheit and beyond. A simple cast aluminum wheel can't handle that. It just isn't strong enough. That's why wheels are forged. Forging is a process where the metal doesn't just take shape, it changes its internal structure. Under enormous pressure, the metal grains reorganize, compress, align. Forged aluminum is stronger than cast aluminum, roughly the same way an oak plank is stronger than pressed particle board. They look similar on the outside, completely different on the inside. It all starts with a billet. An aluminum billet is a cylindrical chunk of alloy, kind of like a thick, short log. Diameter, about 12 inches, height, also around 12 inches, weight, roughly 50 pounds. The material isn't pure aluminum, but a 6000 series alloy, which includes magnesium and silicon alongside aluminum. It's this combination that delivers the right balance of lightness, strength, and forgeability. The billet gets loaded into a furnace and heated to around 800 degrees Fahrenheit. That's below aluminum's melting point. The metal doesn't flow, it stays solid. But at this temperature, it becomes plastic, almost like softened modeling clay. That's the exact state it needs to be in under the press. Not sooner and not later. If the billet cools even a few dozen degrees more than it should, it becomes stiffer, and the forging won't go right. That's why the billet moves fast from furnace to press. And now it hits the press. A hydraulic press with 8,000 tons of force. 8,000 tons! That's roughly the weight of 65 fully loaded semi-trucks stacked on top of each other. All that force concentrates on a single billet 12 inches in diameter. The press descends, it takes a fraction of a second. The glowing hot billet that just looked like a cylinder spreads into a disc in one blow. The metal literally explodes outward, filling the mold. Sparks of scale and steam fly from under the press. The part that was just a rough cylinder now has the recognizable contours of a wheel. The hub in the center, the disc, the rim. All this in one stroke, in 1 second. I watched this several times in a row, and each time I couldn't believe how fast it happens. You expect some long process, and suddenly, bam, and there's a wheel. More precisely, a wheel blank, but the shape is already there, and it appeared instantly. After the first strike, the workpiece isn't done yet. It's heated again and placed under the press a second time for what's called finish forging. This blow refines the geometry to tighter dimensions, smooths out imperfections from the first forging. After 2 strikes, the workpiece already looks a lot like a finished wheel, but it still has excess metal squeezed out between the die halves. That gets trimmed off in a special die, and the workpiece takes on a clean contour. Now comes heat treatment. This is a stage that's invisible but critically important. The workpiece is heated to a specific temperature, held there, then rapidly cooled in water. That's called quenching. Then comes aging, heating to a lower temperature, and a long hold. This entire sequence changes the alloy's microstructure at the molecular level. Magnesium and silicon atoms form tiny hard particles that strengthen the aluminum matrix. After heat treatment, the wheel can handle loads that would tear apart an untreated blank. After heat treatment, the wheel heads to machining. CNC lathes and milling machines remove material from precision surfaces: the tire bead seat, lug bolt holes, hub face surfaces. Tolerances here? Thousandths of an inch. The tire must sit on the wheel with zero gap and zero interference, exactly as engineered. Lug bolts must enter their holes without play. Any deviation in the wheel either won't install or will wobble at speed. Speaking of wobble, one of the most critical tests on a finished wheel is run-out check. Deviation from a perfect plane and circle. The wheel gets mounted on a specialized fixture and spun. Sensors measure how much the surface deviates from the theoretical ideal. If the wheel runs out even a few hundredths of an inch beyond spec, it goes back for rework or gets scrapped. A semi rolling at 75 miles per hour with 45,000 pounds of cargo doesn't forgive wheel runout. Final stage, polishing. Alcoa makes wheels that look like mirrors. This isn't just aesthetics, it's part of the product and part of the marketing. Truck drivers in America take the appearance of their rigs seriously, and a shiny wheel is a sign of quality and pride. Polishing happens in multiple stages with progressively finer abrasives, and by the end the surface reflects your face better than an ordinary bathroom mirror. The finished wheel goes through final inspection, dimensional checks, run-out testing, visual examination, and then to the warehouse, from there to dealers and truck assembly plants across the country. From billet to finished wheel, a few hours of production time and several days counting heat treatment. The result, 29 pounds of forged aluminum that'll serve 1 million miles and more. The finished wheels leave Cleveland for every corner of the country. Some head straight to assembly plants: Kenworth, Peterbilt, Freightliner, Mack, where they're built into new semi-trucks. The rest get distributed to parts dealers from Florida to Washington, because wheels on working rigs wear out too and need replacing. Turns out the Cleveland plant feeds the whole country, both new trucks and those already racking up miles on the interstates. That's the story of one wheel, from a red-hot billet under an 8,000-ton press to the highway somewhere between Texas and California. If you're into watching how the stuff we don't notice actually gets made, subscribe to the channel. There are plenty more stories like this one. I want to say something separate about changing a wheel on the road, because it's not the same as swapping a tire on a sedan by the shoulder. On a semi-truck, wheels last a long time, but when one finally gives out, it's a whole different procedure. First off, the wheel weighs 29 pounds, not something one guy easily spins with one hand. Second, the lug bolts are torqued to 450 to 500 pound-feet. For comparison, on a regular passenger car, it's about 100 pound-feet, meaning the bolt on a semi is tightened 4 to 5 times harder, because underneath that wheel could be 80,000 pounds of cargo moving at 70 miles per hour. There's no room for a loose bolt. That's why the swap is done with a calibrated torque wrench by protocol, and after the change, the wheel is mandatory rechecked after a set number of miles. Simple part, but behind it stands an entire engineering culture.
This single tire stands over 13 feet tall. That's taller than 2 grown men stacked on top of each other. It weighs more than 5 tons, the same as a fully loaded delivery truck, and just one of them costs as much as a brand new luxury car, somewhere north of $40,000. And the machine it's built for doesn't even blink at that. A Caterpillar 797 hauls 400 tons of rock in a single load, riding on 6 of these monsters at once. But here's the part that'll get you. To build just one of these tires, a factory has to cram in nearly a ton of steel and almost 4 tons of rubber, then bake the whole thing for almost an entire day. Stick around, because the way they make a tire this big is wilder than anything you've ever seen on a road. Let's start with the scale, because the numbers barely sound real. The biggest of these, The Michelin 5980R63 measures just over 4 meters across. That's 13 feet of solid tire. It's 5 feet wide. And inside that single tire sits 890 kilograms of steel, enough to build 2 small cars, plus 3,850 kilograms of rubber, enough to make 500 ordinary car tires. 500 from the rubber in one tire. And it has to carry over 100 tons all by itself, because 6 of them together hold up a truck that weighs more than a fully loaded jumbo jet. These aren't really tires anymore. They're load-bearing structures the size of a small building, and they start their life as something you'd never expect. A gooey black soup. It all begins with the compound, the rubber recipe. And it's not just rubber. Workers blend natural rubber, tapped from trees, with synthetic rubber cooked up from oil, then throw in carbon black, that fine black powder that makes the mix tough and gives a tire its color, plus silica, oils, and a list of chemicals each manufacturer guards like a secret. All of it gets dumped into a machine called a Banbury mixer, a giant industrial blender that chews and kneads the ingredients under enormous pressure. The friction alone heats the mixture past 100 degrees Celsius until it turns into a thick, hot, sticky mass. Get the recipe even slightly wrong, and the finished tire could overheat and blow apart under load. So every batch is tested before it moves on. And what comes out is the raw muscle of the tire. But muscle alone won't hold 400 tons. For that, you need a skeleton. And that skeleton is made of steel. Here's something most people never realize. Inside that mountain of rubber is a cage of steel wire holding everything together. It starts at the bead, 2 thick rings of steel cable that wrap around the inner edge of the tire, the part that clamps onto the wheel. These rings have to grip so hard that no amount of force can ever pull the tire off the rim. Then comes the carcass, layer after layer of steel cord fabric, each one laid at a precise angle and crossed over the next. A regular car tire might have 2 of these layers. A giant mining tire can have 40 or more. 40 layers of steel and rubber, stacked into a single wall thick enough to shrug off jagged rock at full speed. And remember that 890 kilograms of steel? This is where almost all of it goes, woven into a skeleton you'll never see, but one that's holding up the entire load. Now the real assembly begins, and it's part construction, part sculpture. The tire is built up on a massive rotating drum, layer by layer, by hand and by machine. First, the inner liner, the airtight rubber skin that holds the pressure in. Then, the steel carcass plies, wrapped on one after another. Then, the beads, locked into place. Then the belts, more steel, laid across the top to keep the tread from flexing. And finally, the tread itself, a slab of rubber so thick you could lose your whole hand in the grooves. Piece by piece, that pile of steel and black goo grows into the rough shape of a tire. At this stage, they call it a green tire. It's the right size, the right shape, but it's soft, weak, and completely useless. Drop it on a truck right now and it would tear itself to shreds in minutes. Because everything that makes a tire strong hasn't happened yet. That comes next, and it involves enormous heat. This is the moment everything comes together, and it's called curing. The soft green tire gets lowered into a colossal mold, a steel press as tall as a room, carved on the inside with the exact tread pattern. The press slams shut around the tire and starts pumping in heat and pressure, climbing to around 350 degrees Fahrenheit, under hundreds of pounds of pressure per square inch. And here's where the scale of these things really hits you. A normal car tire bakes for maybe 10 to 15 minutes. A tire this big? It can sit in that press for up to 24 hours. A full day of cooking, just for one tire. During all that heat, a chemical reaction called vulcanization fires off inside the rubber. The molecules link together into a tight, springy web, transforming that soft black goo into the tough, elastic material that can survive a mining pit. The mold presses the tread and every marking into the surface at the same time. When it finally opens, a finished tire rolls out, just hot enough to burn you. But the factory doesn't trust it yet. Not even close. Because a flaw you can't see, a tiny air pocket or a misplaced wire buried under all that rubber, could make a tire worth tens of thousands of dollars explode on the job. And when a 5-ton tire fails under a 400-ton load, people die. So every giant tire gets X-rayed, shot through with radiation, so inspectors can see the steel skeleton inside and check that every cord sits exactly where it should. Then it goes through a process called shearography, where lasers scan the surface under changing pressure to hunt for the faintest hidden separation between layers. Nothing slips by. Only after a tire passes every test does it get its stamp of approval and head out the door. And that door opens onto a world where these tires earn their keep in the most brutal job on Earth. Here's where it all pays off. That finished tire gets shipped to a mine and mounted onto a haul truck like the Caterpillar 797. 6 tires go on each truck, and together they shoulder a machine that, fully loaded, can weigh over 600 tons. That's heavier than a Boeing 747 at takeoff, rolling on rubber. Every single day, these trucks climb in and out of open pits, grinding over rock that would slice an ordinary tire open in seconds, hauling 400 tons of ore at a time. And the tires just take it. They run for thousands of hours before they wear out. But when one finally does need replacing, it's not a quick job. It takes special equipment just to lift a 5-ton tire into place, and the price tag to swap a full set can run into the hundreds of thousands of dollars. A single set of shoes for one truck costs more than most houses. So the next time you see one of these monsters in a photo, dwarfing the people standing next to it, remember what it actually took to build. Nearly a ton of steel woven into a hidden skeleton, almost 4 tons of rubber blended from trees and oil, and a secret list of chemicals, 40 layers stacked on a spinning drum, a full day of baking inside a press the size of a room, and every one of them X-rayed and laser scanned before it's ever trusted under 400 tons of rock. It's one of the most extreme pieces of engineering on the planet, and almost nobody ever thinks about it. If this blew your mind even a little, subscribe to Made on Earth, because we take you inside the machines and factories that quietly run our world. And go watch how the Gigapress casts an entire car body in 80 seconds next. Trust me, you're not ready for that one. Hey there, friends! Today I'm standing in the middle of a yard that smells like metal, oil, and just a hint of adventure. In front of me sits a machine that casually devours a car faster than I can demolish a hot dog at a baseball game. 9,000 horsepower. Remember that number because we're coming back to it. First, let's figure out where we actually are. This is a recycling facility somewhere on the outskirts of town. The yard covers roughly 18 acres. That's about 18 football fields. Around the entire perimeter lie mountains of scrap metal, old refrigerators, dented barrels, washing machine doors, and of course, cars. Lots of cars. Here it is, the Mega Shredder. In short, it's a massive steel box about 40 feet long, 30 feet tall, and weighing around 600 tons. 600 tons, folks. That's like 50 school buses stacked on top of each other. I'm standing next to it, and my head barely reaches where the loading chute begins. In the States, about 12 million cars get recycled every year. That's the highest number in the world. The metal recycling industry generates around $32 billion annually and employs roughly 150,000 people. Now here's how cars get in here. Next to it, there's a magnetic crane operating, a 70-foot boom with a round magnet about 6 feet in diameter at the end. The operator sits in the cab, moves the levers, and this thing lifts an old sedan like it's a toy from a kid's playset. Lifts it, carries it over, drops it on the conveyor. Boom. The metal crashes so loud my ears are ringing for another 10 seconds. About 200 large industrial shredders operate across the US. The most powerful ones are 9,000 horsepower class, and there are roughly 25 of those in the country. The conveyor slowly carries cars toward the shredder's jaws. Speed, about 20 feet per minute. Seems slow, but there's no need to rush. The machine swallows each car in turn, and if you throw in 2 at once, you might get a jam, and stopping this beast costs money. Big money. And then, the moment of truth. The car reaches the edge, and it gets pulled inside. There, in the guts of this monster, a rotor spins. The rotor's diameter, about 8 feet. Weight, around 72 tons. Hammers are mounted on it. That's right, actual hammers. Each weighs about 300 pounds, and there are 32 of them. The rotor spins at 600 revolutions per minute. 600. Every second, the hammers strike whatever's inside 10 times. What happens to the car? It just gets torn to pieces. In 45 seconds, a whole car is reduced to chunks of metal the size of my fist. 45 seconds, folks. I spend more time boiling water for coffee. The sound is a whole different story. When the shredder's running full tilt, noise levels hit 120 decibels. That's louder than a jet taking off if you're standing 200 feet away. Everyone here wears ear protection, and I slapped mine on too. Otherwise, my ears would be ringing for a week. Now here's where it gets interesting. What happens next? Because what comes out of the machine isn't just some shapeless pile of scrap metal. It's a neatly sorted mixture ready for further processing. And here's how it works. After the shredder, everything lands on a wide conveyor belt with a massive magnetic drum hanging overhead. Diameter, about 4 feet. It spins and pulls out anything containing iron from the stream. Steel, cast iron, all of it flies into one bin. Whatever's not magnetic, aluminum, copper, plastic, glass, keeps moving down the line. Next stop, the air separator. Sounds fancy, but it's dead simple. A powerful stream of air blasts upward at about 40 miles an hour. Lightweight stuff, plastic, fabric, foam from the seats, gets blown sideways into a separate pile. The heavier stuff, aluminum and copper, drops onto the next conveyor. Then comes another cool piece of equipment, the eddy current separator. Let me break it down for you. It's a drum that creates a magnetic field that basically shoves non-ferrous metals. Here's what it looks like. An aluminum chunk literally jumps up and flies into its bin, like someone flicked it with a slingshot. Copper, brass, same deal. Honestly, it looks pretty spectacular. So what's the bottom line? From one car weighing roughly 3,000 pounds, you get about 2,400 pounds of steel, 300 pounds of aluminum, 120 pounds of copper, and around 100 pounds of other metals. The rest, plastic, rubber, glass, doesn't go to waste either. It gets shipped to other recycling lines. Now let's talk productivity. This shredder can process about 400 cars in 1 hour. Per shift, and a shift here is 12 hours, we're talking 4,800 vehicles. Per day, if you ran it non-stop, you'd get roughly 9,600 cars. Of course, in practice, nobody does that. You need time for maintenance, hammer replacement, cooling, but the potential? That's the potential. Speaking of hammers, you know how long they last? About 200 hours of operation. Then they pull them off, flip them to the other side, another 200 hours. Total, one set of hammers runs about 400 hours, then they swap them out. One hammer costs around $800, and there are 32 of them. Do the math yourself on what one replacement cycle costs the plant. Now let's talk electricity. This beast runs on 2 motors, 4,500 horsepower each. Combined, that's our legendary 9,000. In 1 hour of operation, the shredder consumes as much electricity as a small town uses in a day. I'm serious. The facility has its own substation, and even with that, they sometimes get voltage drops when the shredder swallows particularly tough prey, like an old pickup with a reinforced frame. I asked the operator what was the hardest thing he'd ever processed. He laughed and said one word: tank. That's right, folks. They once brought in an old training tank without a turret, but with full armor. The shredder ate it, but slowly, took 20 minutes, and they had to replace 4 hammers that cracked from that particular dessert. Safety is a whole different story. Around the machine, there are vibration sensors, temperature sensors, oil pressure sensors. If something goes wrong, the system automatically stops the rotor in 8 seconds. Stopping 72 tons of steel spinning at 600 revolutions per minute in 8 seconds? That's no joke. The braking system is more powerful than 9 trucks combined. And the last thing I want to point out, this whole story is about recycling. Of the cars that end up here, over 95% of the material gets back into circulation. Steel goes to the steel mill, gets melted down, and becomes a new car, or a beam for a building, or a rail for a railroad. Aluminum, cans for drinks or airplane parts, copper, wires. This is a real second, third, and sometimes even 10th life for metal. Melting 1 ton of steel from scrap saves approximately 2,800 pounds of iron ore, 1,200 pounds of coal, and 120 pounds of limestone. Plus the energy costs for melting scrap, 60% less than producing steel from scratch. When you send your old ride to the scrapyard, you're not just freeing up space in your garage, you're saving enough energy to power an average home for several weeks. I've been standing here for 6 hours. I'm drenched in sweat, my ears are still ringing, my pants are covered in metal dust, but I'm blown away. Because this machine, it's the work of hundreds of people. Engineers who designed it, welders who assembled the frame, operators who battle it every single day. And the result? Mountains of scrap, transformed into material for a new life. If you enjoyed this, hit that like button, subscribe, because in the next video we're heading to the plant where they melt down what we saw today. You'll see a steel briquette become glowing liquid at 2,800 degrees Fahrenheit. See you then, friends!
Every year, millions of tons of ore get hauled by quarry giants weighing over 600 tons. But all that mass is held together by bolts. A single bolt like this weighs 9 pounds, costs over $500, and handles loads exceeding 100 tons. Why is it 20 times more expensive than a regular bolt? And what happens if you skimp on just 20% of its strength? In this video, I'm showing you the metal that decides whether a driver makes it home. Stick around till the end. You'll never look at a bolt the same way again. I stood in this specialized factory that makes fasteners for heavy machinery, holding a bolt that weighed 9 pounds. Length, 80 inches, diameter, 2¼ inches, head, 3 inches across. At first glance, just a regular big bolt. But the price, $520 a piece. The engineer who was showing me around saw the surprise on my face and asked, "You know how much a regular bolt this size costs at a hardware store?" I shrugged. $25, maybe 30. So why is this one 20 times more expensive? Let me show you. It all starts with the material. This is a special alloy steel with chromium, molybdenum, vanadium, and boron added. Tensile strength, 180,000 pounds per square inch. For comparison, regular steel has a tensile strength of 60,000. That's 3 times higher. Raw material arrives as rods 2½ inches in diameter. Each rod comes with a certificate showing the exact chemical composition down to hundredths of a percent. Deviation of even 0.1% in carbon content. And the entire batch gets rejected. First stage, cold forging the head. A 20-inch blank gets clamped into a die and a hydraulic press generates 1,200 tons of force. In 5 strikes, a 3-inch diameter hexagonal head takes shape. Under this pressure, metal density in the head increases 12%. Fibers compress, pores close up. Next, thread rolling. Same principle used for other high-quality bolts. Threads aren't cut, they're rolled under 40 tons of pressure. Metal fibers follow the thread profile, creating a structure 50% stronger than cut threads. Now, the most interesting part begins. Selective heat treatment. Traditionally, the entire bolt is heated and hardened uniformly. But for haul truck bolts, that won't work. The head needs to be ultra hard to withstand contact pressure from the wrench. And the body needs to be tough to absorb shock loads. The solution? Induction heating. The bolt gets placed in a special coil carrying high-frequency alternating current at 10 kHz. The alternating magnetic field induces eddy currents in the metal's surface, heating only the head and the top 3 inches of the bolt's shank. I watched the process through protective glass. At first, nothing happened. Then the bolt head started glowing dull red, then bright orange, almost yellow. Peak temperature in the head hit 1,650 degrees Fahrenheit. Meanwhile, the bolt body, just a few inches below, stayed dark. Temperature there never exceeded 300 degrees. The entire heating process took 30 seconds. Speed is critical. More heating lets the heat spread along the whole length of the bolt, and the selective effect disappears. The moment the right temperature hit just the needed spot, the bolt was instantly plunged into a bath of polymer quenching solution. The sharp temperature drop transformed the metal structure in the head into super hard martensite. Rockwell hardness, 58 units. That's almost like a hardened knife blade. But the bolt's body stayed pretty soft and ductile. Then the bolt gets tempered, heated to about 150 degrees and cooled freely. This relieves internal stress while preserving hardness. Final head hardness, 54 Rockwell units body, 38. Perfect balance. Next stage, marking. Numbers are stamped on the bolt head, 12 and 9. The engineer explained what this means. The first number, multiplied by 100, that's the tensile strength in megapascals. 12 times 100 equals 1200 megapascals, or 180,000 pounds per square inch. The second number is the ratio of yield strength to tensile strength, multiplied by 10. 9 means the yield strength is 90% of the tensile strength. This means the bolt only starts to deform when loaded to 162,000 pounds per square inch. For comparison, a regular bolt from a hardware store is marked 5 and 8 or 8 and 8 at most. Strength, just 50 or 80,000 pounds per square inch. Put a bolt like that on a Caterpillar 797F and it'll snap the first time you hit the brakes. But here's the most impressive part, quality control. Every single bolt, no matter the size, goes through ultrasonic testing. I watched as the operator placed a bolt into a special rig, where ultrasonic sensors scanned it along its entire length. The principle is simple. Ultrasonic waves at 5 MHz pass through the metal at 19,400 feet per second. If there's a crack, void, or other irregularity as small as 0.02 of an inch inside, the wave bounces back from it, and the detector picks it up. And you should pick up a subscription to my channel, please. On the computer screen, I watched the bolt's profile in real time. Green zones, the metal's uniform. Yellow, minor inclusions but within tolerance. Red, critical defect, bolt rejected. Out of a batch of 500 bolts I saw, 9 got scrapped. That's nearly 2%, an astronomical figure for mass production, but acceptable for critical components. Each accepted bolt gets a unique number laser engraved on the head. That number lives in a database with its complete manufacturing history. Batch number, production date, results from every test. If a bolt fails on a truck in Australia 5 years from now, engineers can trace its entire history in minutes. The mechanical testing is even more brutal. Every 25th bolt goes to destruction. The machine pulls it with force increasing by 2,000 pounds per second. The spec requires the bolt to withstand 450,000 pounds. They actually break at 520,000, a 60% safety margin. Another test is cyclic fatigue. The bolt gets torqued to 2,000 foot-pounds, then stretched with 200,000 pounds of force, then released. This cycle repeats 2 million times. The bolt must show 0 signs of fatigue. No cracks, no elongation, no loosening. Why such brutal requirements? An engineer showed me footage from a mine in Western Australia. A Caterpillar 797F rolling at full load. 400 tons of ore in the bed plus 200 tons of its own weight. Speed, 35 miles per hour, miles per hour. The driver suddenly spots an obstacle and slams on the brakes. 600 tons of inertia tries to keep moving forward. All that force transfers through the suspension to the wheels, and from the wheels to the bolts holding the rims. During braking, each bolt generates a load of 180,000 pounds. That's 109 tons on a single bolt. If just one bolt out of 24 on a single wheel snaps, the load redistributes to the others. They get overloaded and start failing in a chain reaction. The wheel flies off. A truck moving at 30 miles per hour with 600 tons loses control and rolls over. In 2016, exactly this kind of accident happened in Chile. They'd used the wrong grade of bolts. Formally, the difference was small, 20% less strength. But that 20% was enough. During emergency braking, 3 bolts snapped. The truck rolled. 2 dead, $8 million in damages. After this accident, bolt requirements became even more stringent. Quarry statistics show one Caterpillar 797F haul truck uses 96 bolts to secure its wheels. Over a year, they're tightened and stretched under load millions of times. Every 2,000 hours of operation, roughly a year, the bolts are replaced regardless of visible condition. A full set costs $48,000. But the cost of internal downtime if the truck fails? $100,000 a day. So $500 per bolt isn't manufacturer greed. It's the price of absolute reliability. Each bolt goes through dozens of manufacturing and inspection stages. The finest steel, the tightest tolerances, the most rigorous testing. And after all that, they're swapped out long before their theoretical service life ends.
This machine weighs 8 million pounds and replaced 70 welding robots with a single part. Most engineers still think it's crazy when they hear about it, and no wonder, because if the aluminum overheats by just 5 degrees, the part crumbles to dust. If the press releases by a millimeter, liquid metal explodes outward at 16,000 pounds per square inch, 6,000 tons of force. 2 minutes from molten metal chaos to a finished piece of body. I'm going to show you everything from the inside, how it works, why it's the edge of what's physically possible, and why the entire auto industry is watching with their jaws dropped, but still too scared to copy it. Look at this monstrous press. It's as long as a small city block and weighs more than 8 million pounds. We're used to the rear end of a car being welded together from 70 or 80 separate steel parts. That's time-consuming, it's expensive, and every weld point is a potential spot for rust or failure. The GigaPress just takes all those 70 parts and replaces them with one giant cast piece. It saves a ton of time, but creates such a level of complexity that most engineers around the world still tap their finger against their temple when they hear about it. It all starts with molten aluminum. The temperature here holds at 1300 degrees Fahrenheit. It's a real lake of fire, boiling behind the wall of a special furnace. Aluminum is tricky stuff. If it overheats by 5 degrees, the part will be brittle. If it cools too fast, it'll crack right inside the press. Every few seconds, a giant ladle grabs about 180 pounds of liquid silver metal and injects it into the press chamber. It's a breathtaking speed. The metal flies into the mold at over 200 miles per hour. Try to feel this moment. 180 pounds of liquid flame filling a complex mold in a fraction of a second. Now for the main conflict in this process. The mold, where metal gets injected, weighs hundreds of thousands of pounds and is made from ultra-high-strength steel. When molten aluminum blasts into it at 16,000 pounds per square inch, the mold wants to split at the seams. This is where the GigaPress shows its true power. It squeezes these two mold halves with 6,000 tons of force. It's like you stacked 135 Abrams tanks on top of the mold and held them there motionless. If the press loosens even a millimeter, liquid aluminum shoots out under insane pressure, and it turns into a real explosion. But pressure is only half the problem. The biggest enemy here is air. Any tiny bubble inside the part makes it weak. So before injecting the metal, powerful pumps create an almost complete vacuum inside the mold. This entire process, from vacuuming to injection to solidification, takes less than 2 minutes. It's brutal stress on the equipment. Every second, the press components expand from heat and compress under pressure. Few metals in the world can handle this kind of operation 24 hours a day. This body casting technology demands a level of sterility and control from the factory that simply didn't exist in the auto industry before. The aluminum alloy we use has to be perfectly clean. If even a single speck of iron or other debris gets into the crucible, the entire batch of metal, worth thousands of dollars, goes straight to scrap, because the part won't pass strength tests. When the molten mass flies into the mold at speeds over 100 feet per second, every millisecond of delay can cause the aluminum to start solidifying before it fills all the channels. When the mold opens, a massive robotic arm pulls out the hot part. It's still glowing from the heat, and you're looking at a perfectly smooth piece of body structure that used to be assembled by hundreds of welding robots. It looks like we just printed a chunk of car in real time. But there's no room to relax. Every part immediately goes into a bath of cooling fluid, then under X-ray. Any internal crack invisible to the naked eye sends this expensive piece straight back to the melt. 1% defect rate in a production like this, that's already massive losses, so quality control here is tighter than in the space industry. So why doesn't everyone do it this way? Because it's insanely expensive. If you mess up the car design, you can't just reprogram the welding robot. You'll have to scrap a $5 million mold and order a new one, which takes 6 months to make. The GigaPress doesn't forgive engineering mistakes. It demands absolute precision at the computer drawing stage. This is technology for those who are 1000% confident in themselves. That's why you feel such tension in this hall. Every second the press operates brings either massive profit or colossal losses. The machine itself is maintained by an entire team of specialists who monitor aluminum purity and mold lubrication. Before each injection, robots spray a special mixture on the mold walls. This prevents the part from sticking to the steel like scrambled eggs to a bad pan. Too much lubricant, it'll leave stains on the metal. Too little, the part gets stuck, and you'll have to disassemble this multi-ton device by hand, which takes weeks. It's a constant balancing act on the edge. We're looking at a real triumph of rationality over tradition here. Before, factories had hundreds of robots sparking with welding, taking up acres of space and demanding constant attention. Now we see a single shop floor with a couple of these giants doing the work of an entire factory. It looks like a scene from the future, where manufacturing becomes cleaner, faster, and far more sophisticated at its core. You get a car that's 40 pounds lighter, stronger in a crash, and simpler to repair. Though that last part's debatable, if you dent a cast part like this, you're not straightening it out with a hammer. Plenty of skeptics said casting huge aluminum parts like this was impossible. They claimed the metal would flow unevenly, or the mold would wear out too fast. But these silvery blocks coming out of the press every 2 minutes prove otherwise. It's a victory of boldness over caution. We're watching tons of steel and insane pressure force the material to bend to the engineer's will. This isn't just a chunk of iron, it's a massive laboratory where physics and metallurgy operate at the edge of what's possible. Look at these massive pistons and hydraulic hoses thick as a human leg. They carry enough energy to power a small town. When the press hits, the building around it shudders slightly. This is the rhythm of the modern world. We've learned not just to assemble things, we've learned to create them from the chaos of molten metal in a single touch. This makes manufacturing greener because we use less energy on welding and recycle all the aluminum scrap right on site. Every trim, every rejected sheet falls into the chute and returns to the furnace to become part of a new machine again in an hour. This process mesmerizes with its brutality and elegance at the same time. You see enormous force tamed by computer algorithms. This is real high-tech in heavy industry. While others argue about software, here people work with actual matter, changing the very essence of how we create things around us. I hope you found watching this monster as fascinating as I did. We saw how one cast part replaces hundreds of components and understood why this is so complex and expensive. This is the Industrial Revolution right before our eyes. Thanks for watching. Hit that like button if you're into this kind of scale, and subscribe to the channel. We'll find even cooler facilities around the world. See you on the next tour, where we'll break down complex things into simple atoms again. Until next time.